Welcome back. We're continuing to look at graphing reciprocal functions. In our last video, we looked at graphing a reciprocal function when we had kind of some other values going into it. And it was a little bit more complicated. We had to kind of consider a variety of things. In this video, we are going to take this back to our transformations of functions, which we've looked at all year. So if I look at my reciprocal function in the form of y is equal to a over x minus h plus k, with the parent function y is equal to 1 over x, and my general shape looking like this, the shape of my parent function looking like this, with vertical asymptote at x equals 0 and horizontal at y is equal to 0. If I look at this, my transformations a, h, and k are exactly as they've been all year. So a is going to be a vertical stretch or shrink. It's also going to be a reflection across the x-axis. And this one is if a is negative. So if a is negative, it's going to flip our graph across the x-axis, which is what it's always done. And if a, the absolute value of a is bigger than 1, it's going to be a vertical stretch. If the absolute value of a is between 0 and 1, it's going to be a vertical shrink. H is going to do the same thing that it's always done, which is going to be a horizontal shift or a horizontal translation. So x minus h, it's going to move h units right. And for k, k is going to be our vertical shift. What ends up becoming kind of neat about h and k is because our graph starts with vertical and horizontal asymptotes at x equals 0 and y equals 0, when I shift my graph h units to the right, my vertical asymptote becomes x is equal to h, and my horizontal asymptote becomes y is equal to k. So h and k become really, really important factors. So if I look at my last graph that we did, if I identify a, h, and k in this graph, a is equal to 2, or I'm sorry, a is equal to 1, it's that numerator up there, h is equal to 2, x minus h, and k is equal to 1, my vertical asymptote is at x is equal to h, and my horizontal is at y is equal to k. So all of these are going to become really, really key things when we are looking at our graph. So if this is the function I'm looking at, and I now know what a, h, and k are, my domain and range, the domain of this graph is going to come from the denominator can't be equal to 0. So, and it's also a shift of my parent function, which my parent function had, the domain is x can't be equal to 0. If I shift that h units, my domain becomes x cannot be equal to h, and my vertical asymptote becomes x is equal to h. The range of my parent function was y can't be equal to 0. If I shift that, my new range is y can't be equal to k. My horizontal asymptote is at y is equal to k. My x-intercept, I'm still going to need to plug my values in. So my x-intercept, I'm still going to need to plug in y is equal to 0. So it will be some x value 0. And my y-intercept is still when x is equal to 0. So that's at 0 and then some y value. But my shape is going to be dependent on a. If a is positive, these are my vertical and horizontal asymptotes. If a is positive, my graph will look like this. Okay, so as expected, y is equal to k, x is equal to h, and I'm in the top right and bottom left portions of my graph. If A is negative and my graph flips across the x-axis, so if this were to flip over, what ends up happening is my graph looks more like that. So what ends up happening, if A is negative, my graph is going to be in the bottom right and top left quadrants, like that. So if my A value is positive, my graph will look like this. If my A value is negative, my graph will look like that. Once I know that information, once I have this idea of what's happening, these graphs become really easy. We're just going to identify A, H, and K. H and K will give us our asymptotes. Our value of A will let us know what shape we're looking for, and then we can go ahead and make a table of values with 3 points in each section of the graph.